Another particulate drawing that we have for an AP exam question, and in this case we have HF, which is hydrofluoric acid, and we're mixing it with water, and we have an equilibrium here. It's got H3O plus, this is the hydronium ion, and the fluoride ion. Now you should know, again, the strong acids, and let me pull them up. Let me just go to our Chem Advantage site and our summary. And the strong acids are HCl, Bri, the halogens, but HF isn't in here. HF is a weak acid. It's a little bit difficult to explain why, but it is a weak acid. It's got some very strong bonds to its H, so it won't release them. Nitric, sulfuric, and of course perchloric. These are our strong acids, and notice they've got these little bubbles on them because they completely ionize. All of the other acids are considered to be weak acids, that they hardly end up producing H3O+. They stay pretty much as their weak acids. Now, one extra thing I thought I should bring up is in terms of hydrofluoric acid, it's really a very dangerous acid, not because it's strong in terms of producing hydronium ions, but it's very poisonous. It tends to dissolve glass, and it'll even dissolve things like rocks. Interestingly, it's stored in a plastic container. It doesn't react with the plastic. And notice here they show it as HF, and when it reacts with water, it produces hydronium and fluoride ions. And acidified fluoride ions, very, very, very nasty in terms of being poisonous. Do not work with hydrofluoric acid unless you've got a week's worth of training and have a suit that is impervious to it. Have your lab partner work with HF. You don't want to work with it. It's an insidious poison, and very often if you have an accident, there's no way they can save you afterwards. So stay away from hydrofluoric acid. But except for this problem, let's get back to it. This is our problem where we have some hydrofluoric acid. They show you the HF. Again, we've got our fluoride, we've got our hydrogen ion, but they're missing the water in it. Now, this diagram is pretty nice in that it shows once it's at equilibrium, we just have one of these HFs turn into a fluoride, and you might say, well, what's this? What's this H3O+? Where'd that came from? That's because they didn't show you the water molecules. Let me show you the water molecules, and actually they sort of make things more difficult. Let me pull this out, and we'll look at the diagram now. In a solution, HF in water, where you see the water molecules, there are going to be water molecules all over the place. Here's our HFs. We have 8 of them. And I put in 8 waters, but really there'd be like 100 of them, and I'm not going to draw those in. And this pretty much stays the same way. I mean, we've got most of the HFs are going to bounce against this water and do nothing. The H plus will stick to the fluoride. HF is a weak Bronsted acid. It doesn't donate this H plus. Now notice over here, I've taken this HF and had it react with one of the water molecules. So it gave its proton to the water molecule, an H3O+. So you're going to have a little bit of hydronium ion, and you'll have your fluoride ion here also, which if it runs into this hydronium, will pick up the H plus again. In fact, that's our equilibrium. The fluoride, which is a pretty strong base, will pick up the proton from the hydronium and turn into HF. It will act as an acceptor of a proton. And that's why we have this equilibrium, because these fluorides will react with the hydroniums to change the hydronium into water and keep the H plus to itself. That's our equilibrium. So in this example, only 1 out of our 8 HF molecules produced hydronium ions. So if we have 1/8 of these HF molecules actually making the acid, so if you had 8 molar HF, which you do not want to work with, you'll only end up having 1 molar H plus acid. Only 1/8 of it actually becomes the acid. This is the thing about weak acids, is that they don't really produce a lot of H3O+. So In this case, in this concentration, we have 1/8 of the HF actually acting as an acid. So, as I said, stay away from hydrofluoric acid, especially if you're glass.